welcome back. In the last video, we covered the first question of the 2018 AP Chemistry exam, and now we're gonna move on to the second question. So let's get started. Here's the question number 2. A student investigates the reactions of nitrogen oxides when the reactions in the investigation requires an equimolar mixture of NO and NO2, which the student produces using the reaction above. The final product is represented in this box here, and they want us to draw out the reactant mixture. So how you would go about doing that? First, you have to figure out what in the world am I left with? What do I have to be able to produce? So in terms of NO, we have 1, 2, 3, 4 NO remaining. And we have created 1, 2, 3, 4 NO2. So we know that whatever is in here, we have to at least have the 4 NOs that were never changed. So let's draw those in now so that we don't forget. So 1, 2, 3, 4. Okay, now we have to figure out how many NOs and O2s were required to make those 4 NO2s. So we know that 2 NO plus an oxygen makes 2 NO2, except we made 4 NO2. So to get to there, that reaction had to occur 2 times. So we just times each of the coefficients by 2. So you needed 4 NO and you needed 2 O2. Okay? So if we draw those in, we have to add in 4 more NOs. So 1, 2, 3, 4, and we have to add in our 2 O2s. Okay, and that's that. Okay, moving on. So now the student reads in the reference text that NO and NO2 will react as represented by the equation below. Thermodynamic data for the reaction are given in the table below the equation. So this is the information about the energy, and this is the equation that will occur. So the student begins with an equimolar mixture of NO and NO2 in a rigid reaction vessel. That means the volume will not be changing, and the mixture reaches an equilibrium at 298 kelvins. Calculate the value of the equilibrium constant for the reaction at 298 kelvins. So if you look at your data booklet, given the information that we are given, and the fact that we want to find an equilibrium constant, the best equation to use is the one for Gibbs free energy. So that is Gibbs free energy is equal to minus RT ln K. Okay, where R is your gas constant, T is your temperature, and K is your equilibrium constant. So what I like to do is I like to isolate for K first before plugging in all of my numbers. So if we just move your minus RT over, you'll get ln K is equal to Gibbs free energy over minus RT. Okay? Now, the inverse of ln is e to the power, so the constant is equal to e to the power of, and I'm just going to write this out in one line so that it's a little bit easier, minus Gibbs divided by gas constant times temperature. All right, so now let's plug in our numbers. So K is equal to e to the power of, and Gibbs free is up there. So, but you have to remember that we want our Gibbs free energy in joules. So right now we're in kilojoules, so we have to change that to joules. So that would be 870 divided by, and your gas constant is 8.314 times your temperature, which is 298. Okay, so that is equal to, so 8.314 times 298 is equal to 2477.572. So that's equal to minus, so 870 divided by 2477.572 is equal to negative 0.3511. And then final answer is 0.739. Okay, so that's your equilibrium constant at 298 kelvins. Okay, so next, if both the pressure of NO and NO2 in the vessel is initially 1 atmosphere, will the pressure of N2O3 at equilibrium be equal to 1 atmospheric pressure? So, essentially, if you think about gases, if you have 1 atmosphere of that and 1 atmosphere of that, but you combine them to create N2O3, if everything is being used, you'll end up with 1 atmosphere. Okay? Except, what is the point of the equilibrium constant? So the equilibrium constant tells you how much of the reactant will be created into a product. So how much of it will be used, okay? This equilibrium constant is suggesting that there will be a lot of reactant left at equilibrium. Therefore, there will be some left over here and some left over there. So no, there will be more than 1 atmospheric pressure of N2O3 because the reaction is not fully completed. So that was a lot of words. So we write it out. Essentially what we're saying is that so basically, yes, it would be if the reaction went to completion, everything was used up, but at equilibrium, that doesn't happen. Therefore, no, the pressure of N2O3 will not be 1 atmospheric pressure. Next bit. Okay, well, so the student hypothesis that increasing the temperature will increase the amount of N2O3 in the equilibrium mixture. Indicate whether you agree or disagree with this hypothesis. So if we go back here, this is our equation. So, oopsies, sorry, NO plus NO2 becomes N2O3. And if we take a look at our enthalpy change, it's negative 40.4. So what does that mean? Negative. That means that energy is leaving the system. So energy is on this side. Okay? Now, that means that this is an exothermic reaction. Energy is being lost. As a result, if you increase the temperature, essentially you can think of that as the same as increasing one of the components of the reaction. You're increasing the energy here. You are putting more energy into the system. As a result, you're actually going to shift left. So because it's an exothermic reaction, an increase in temperature equals a shift left, okay? Which is the same as a decrease in N2O3. Okay, so therefore we disagree with this hypothesis. Just because you increase the temperature does not mean that all reactions will go further to the right. It depends on which side your energy is. If it's an exothermic reaction and energy is being lost, an increase in temperature will actually shift the reaction to the left and therefore decrease the product that is produced. Whereas if it's an endothermic, this hypothesis would be true because then energy would have been on this side and then it would shift it right. Okay? So therefore we disagree with this hypothesis. And I hope you found this video useful. For more videos like this, please be sure to subscribe to our channel, the link to the right. If you are looking for some one-to-one help, check out the link in the description below where you can have test lessons with either myself or another member of our AP team. I hope you enjoyed the video. Thank you so much for watching.